Good morning. I am Sri Y.K. Mohanta, lecturer in chemical engineering in the Department of Chemical Engineering, UCPS, BERHAMPUR. So, today we are going to study about an important subject, mechanical operation, in which size reduction carries an important and a vital part. And this is important in all kind of industry, including in pharmaceutical industry, as well as if you go for any kind of chemical industry where the size reduction is much more important. So in this aspect we will discuss about the importance of size reductions, its objective and its advantage and disadvantages, what are all equipments used operation. So moving to the what is the objectives of this. Before objective we'll study about the what is mean by a size reduction definition. So definition of size reduction says it is the operation carried out for reducing the size of bigger particles into smaller, or we can say into desired size and shape, with the help of, this is important, with the help of external force. So this is very important. With the help of external force, if we bring a bigger size material into smaller size or our desired size, that we can call it as size reduction. It is also called as, it is also termed as comminution. The size reduction can also be called as comminution in the engineering and technical terms. Now, what is the objective of size reduction? Objective of size reduction. So what are the objective of size reduction? We can tell the objective of size reduction are, the very first important thing is to increase the surface area. So whenever we go for any increment or any reduce in the size, it increases the effective surface area of the element. Why it is important? Because in the chemical engineering field, the reaction that generally happens in the surfaces. Suppose I want to react a bigger size, a football size ball with with some chemical, so it will take very long time to react. But if I crush it into smaller sizes, and the same thing, if I will try to react with the same chemical, it will react very easily. So definitely increasing in the surface area will help us to accelerate the rate of reaction. The next important thing is break the material into smaller sizes in order to separate the most separate the valuable component out of it. So let's say I will take some example, some ores that contain some of the important materials inside it. So unless until we crush them, we cannot separate the valuable things out of these ores. Next, the one of the important thing is to dispose the solid waste easily. So if we see, there are a lot of solid wastes are producing, but if we crush them into smaller size, it can be disposed of very easily. To improve the handling characteristic, what it means is, when we reduce the size of it, we can handle the material very easily. If I take an example, if suppose a big tree is there and it has to be transported in a truck, so if you load the entire tree into one truck, it might not be convenient, or the space of the truck might not be utilized fully. But if we reduce its size into smaller sizes, then we can fill the every part of the truck with that woods, and we can transport it very easily. It will be convenient to handling also. Now, to improve dissolution rate, what does it mean is, suppose I want to mix a sugar cube of 1 centimeter by 1 centimeter by 1 centimeter in a glass of water. It will take very long time to dissolve. But if I can crush it into very smaller sizes, and within some minutes or within a minute we can dissolve it. So these are the importance of size reduction. Next, what are the disadvantages? When there is advantage, there will be also disadvantage. So what are the disadvantages with this size reduction? We will go. First thing is contamination. So when there will be size reduction will be there, then there is a huge chance of contamination. Second thing is drug degradation. If we are crushing a drug into smaller pieces, there is a huge chance that this drug will be have a more contact with the atmospheric air and atmospheric condition. So there is a lot of chance that this will go for easier degradation. Apart from that, if we go, the disadvantage will be lot of, when in the process of size reduction, lot of pollution will be there. If it is not done in a controlled environment, then there might be a pollution where the smaller particles will fly into the air, and this will cause a air pollution. Next, there will be some noise pollution also. The first one will be the air pollution, then there will be a noise pollution. Apart from that, there will be some loss of energy is also there. So size reduction is a very energy consuming process, so it will consume lot of energy. Now what are the mechanism mechanism of size reduction. So what are the mechanism through which we can reduce the sizes? The first one will be the impact. As the name suggest impact means, I say, sudden applying of force. So it's a very, in a very small time, if we apply large force, that will be called as impact. So example, hammer. In hammer, we apply the force in a very short duration of time, and that will be called as impact. The second thing will be attrition. Again, the attrition is nothing but the rubbing action through which the particles surface will reduces into small particles, and if it continues, then the entire material will go into smaller particles. Then cutting. As the name suggests, the cutting means if the materials are easy to cut or they are very soft things, then we can reduce by cutting, also using sharp blades. Next, we'll move to what are the mechanism and law of size reduction. What are the mechanism and laws of size reduction? So this mechanism says the energy requirement for a particle size reduction is a function of input and output of the particle size comma, it also depends upon the hardness and some other particles, some other properties. So what it says, the mechanism which says it depends upon the what is the particle size. First of all, it depends upon the input and output of the particle size. It depends upon the hardness of the material and also some other properties of the materials, like whether it is a wet material or a dry material, or there are some other things which we will study in the coming minutes. Now, there are various theories which suggest how much energy is required for crushing or how much energy is required for the size reduction. So there are three theories are there. Theories associated with size reduction. First is Rittinger's law. Second is Bond's law. Third is Kick's law. So there are three laws which associates with the size reduction. So we'll study one by one. First we will move to Rittinger's theory, or simply we can say Rittinger's law. So this Rittinger's law suggests according to this law, the energy required for size reduction of unit mass is directly proportional to the new surface that is produced, or new surface area produced. So what we can write, that the energy E which is required to crush a material, that is nothing but it is equal to Kr into Sn minus Si, where Sn is equal to the new specific surface area, Si is nothing but this is equal to initial surface area, and Kr is nothing but Rittinger's constant, and E is nothing but, as this is required, that is called the energy that is required. E is nothing but energy required to produce a new surface area from the initial surface area, that is Si to Sn. So this is what Rittinger's law suggests. After that, the second theory, that is Bond's theory, or we can say the Bond's law. So what Bond's law says, according to this law, the energy that is required is proportional to the energy is required to produce a new surface area or produce a new particle is inversely proportional to the square root of the diameter of the product particles. So what it suggests, it says the energy that is required is proportional to inversely proportional to the square root of the diameter of the product particles. So we can say the energy is equal to Kb into 1 by under root the diameter of the product. So where E is nothing but energy required for crossing, Kb is nothing but bonds constant, dp is nothing but diameter of the product. So this is what about the bonds law. Next we'll move to the third one, that was our Rittinger's theory or Rittinger's law. Rittinger's law. So what Rittinger's law says that Rittinger's law, he was also a scientist who has given some size reduction the theory. It says the energy required for reduction in particle size of a solid is directly proportional to the increase in the surface area. Increase in the surface area. So what it says, the E is nothing but it is proportional to the increase in surface area. So which is SA minus SB. What is SA? The SA is the initial surface area, and SB is nothing but the final surface area. So SA minus SB will be the my increase in the surface area. So what I can say, E equal to KR into SA minus SB. So KR is nothing but the Rittinger's constant. SA is the initial surface area, SB is the final surface area. So these are the laws that are given by three scientists: Kick's law, Bond's law, and Rittinger's law. Okay, I think we forgotten the Kick's law. So moving to the Kick's law. So we have repeated the Rittinger's law. So we'll move to the Kick's law. So what Kick's law says, this Kick's law, we'll discuss about this. Kick is a scientist who has given this formula. So Kick's law says the amount of energy required to crush a given quantity of material to a specified fraction of its original size is the same. Just mark it down. To a specified fraction of its original size is the same. Means suppose I'll reduce my size from 100 millimeter to 10 millimeter, which is the ratio of 1:10 or 10:1, or 50 millimeter to 5 millimeter diameter, that is also 1:10 or 10:1 ratio. Then it says it is the same amount of energy will be consumed. So But the mathematical expression says the E is equal to K to log D initial by D final. So this is given by K, so I can say Kk. So Kk is nothing but Kick's constant. Di is nothing but initial diameter. Df is nothing but final diameter. So these are the three laws that are given by Kick's law, Bond's law, and law. Now, if according to Kick's law, if I solve one problem, then you can easily identify what Kick's want to mention through his law. So, I'll take one example. What is the ratio of energy consumed as per Kick's law? Kick's law. Kick's law for size reduction. For size reduction of the same material from particle diameter (100 millimeter to 10 millimeter) and 60 millimeter to 6 millimeter. So if I solve this problem, by using Kick's law, then I'll write the Kick's law. What Kick's law suggests? It says the energy consumed is nothing but Kk into log di by df. So I'll take case 1. So in the first case, my size reduction Kick's law, di is nothing but it is from 100 millimeter to 10 millimeter. So di is equal to 100 millimeter. The final is 10 millimeter. So I will note it as E1. So energy for E1 for the first case will be E1 is equal to Kk or Kick's constant into logarithm of di is 100 by df is 10 millimeter. So if I do, it comes as E1 is equal to, this will get cancelled, log 10 which is equal to 1. So that is nothing but Kk. Now with the same material, so we will use again case number 2. It says we will write E2 is equal to Kk. It's the same material, so there will be no K2. Again log di by df. So here di initial diameter for the second case is nothing but 60 millimeter and df is 6 millimeter. So di will be my 60 millimeter and df is nothing but 6 millimeter. So if I calculate this E2, so this E2 is equal to Kk into logarithm of 60 by 6. So which is nothing but Kk into logarithm of 6 10 so it will be 10. So which is nothing but logarithmic 10 is equal to 1. So it's again kk. So it is asking what is the ratio of E1 and E2. So if I will take E1 from the previous case 1, so which is E1 equal to kk and E2 equal to kk. So if I do E1 by E2 is nothing but again kk by kk, which again get cancelled, so it will be 1. So we can understand from this particular example is that whether we are reducing our sizes from 100 millimeter to 10 millimeter or 60 to 6, whenever the ratio of the diameter of the reduction remains same, at the same time we will get the same energy that is required. Alright, so these are the laws of these are the laws that which associate with the size reduction and or that is nothing but comminution. So with this we are closing today's period or today's lecture. We will meet again in the next class. Thank you. Bye bye and take care.